The last topic in this chapter is called geometric series. It's somewhat similar to arithmetic series, except there is something called as a common ratio, not a common difference. Let's start. So the sequence 7, 14, 80, 28, 56, 112 is called a geometric progression. Each term is a double the preceding term. So therefore, there is something called as the common ratio. The constant multiple is called the common ratio. And hence the notation used for a geometric progression is somewhat similar. So A will be the first term and R is the common ratio. So here you can notice that from this term to this term, there's the difference is like 7, but also if you think about it, this is double of this and this is double of this, and therefore they have something called as a common ratio between them, and hence the first 5 terms of a geometric progression whose first term is A and common ratio is R. A is the first term, AR is the second term, AR squared is the third term, and AR cubed fourth term, and AR to the power of 4 is the fifth term. If you want to find the common ratio, in this one you don't subtract the terms. Instead, you divide the terms. So to find the common ratio, you have to do term 5 divided by term 4, or term 4 divided by term 3, and so on. So that's the principle here. There's something called as common ratio and not the common difference. So if you know that difference, you'll be fine for this chapter. And then we have the sum of a geometric progression. So there are two ways in which you can represent them. Both of them will give you the same answer. So it can be shown that the sum of a geometric progression, Sn, will use the same notation here also, which is A multiplied by 1 minus r to the power of n divided by 1 minus r. R is the common ratio and n is the number of terms. Or you can just write this as A multiplied by r to the power of n minus 1 divided by r minus 1. Either way, you're going to get the same thing. Now let's go to the proof. So first we'll write Sn as normally. So similar to arithmetic progression, here we have to write down each term and sum them up. So it's like A plus AR squared, AR cubed, and so on. And the next line we'll write R into Sn. So we get AR plus AR squared, and so on. When we subtract 2 from 1, we get the following. So when you subtract this, you're left with this term and this term. And therefore, you can take Sn as common here, and then when you divide it, you get the sum. And therefore, this is how you derive it. And if you multiply the denominator by minus 1, you get the alternate formula as Sn is the opposite of that, which is this. This. So that's how you prove it. There is something called as the infinite geometric series. This is a series where the geometric series will converge, meaning it gets smaller and smaller and smaller. So you can find the sum of these, and the reason behind this is because as the number gets smaller and smaller and smaller, if you add the term, it's so insignificant that it won't contribute to the sum, and therefore if it has a common ratio between -1 and 1, and they're not included, that means it will get smaller and smaller and smaller. It becomes so small at a certain point that it's insignificant, and therefore you can find the sum of a geometric series. So an infinite series is a series whose terms forever continue. Continue forever. So the geometric series where A equals 2 and R equals to 1, sorry, this is 1 by 2. Okay. So this is the series. It will continue on, and then the number becomes so small at some point that it does not even matter that much. So now we're gonna talk about like how to find it and like the sum to infinity. So this is an example of a convergent series, like I told you, because the sum to infinity converges to a finite number. And if we consider the geometric series a plus ar squared plus ar cubed and so on, we have to consider this. So, and then if you want to find the sum, we use the normal formula that we talked about here. And then if the number is between -1 and 1, like I told you, then n gets larger and larger, and r to the power of n gets closer and closer to 0. Just think about like half to the power of like 1,000. What will it become? It becomes so small, right, that it approaches 0. And therefore, we know that as n approaches infinity, r to the power of n becomes 0. And therefore, using this principle, we derive that the sum to infinity will be a divided by 1 minus r, provided that r is in between -1 and 1. And so if it's in between 1 and -1, that means the geometric series will definitely converge. Okay, now you might be wondering why a divergent series we can't like find the sum of a divergent series. This is because consider that now r is 2. It will get like bigger and bigger and bigger. So you can't really like find a number because it doesn't converge to like a finite sum. It will keep getting bigger and bigger as you like find the terms. And therefore, this only works for a convergent series, or when like in our case, it should be between -1 and 1. The second and the fourth terms in a geometric progression are 108 and 48 respectively. So let's write that down. So T2 is 108. We know that T2 is AR, so it's 108. And the fourth term is T4 is 48. So we know that A into R to the power of 3 is 48. So given that that all the terms are positive and the first term, find the first term and common ratio. Okay, so let's find that first. If this is 1 and this is equation number 2, if we divide equation 2 divided by equation 1, we get r squared is 48 divided by 108. We get 4 by 9. And therefore, r is plus or minus 2 by 3. But it's given that all the terms are positive. Therefore, r is going to be only 2 by 3. So this is the only answer. And now if you want to find a, we just substitute that. So we get 108 divided by the answer. So therefore, we get a is 162. And now if we want to write down an expression for the nth term, we get Tn equals a, which is 162, multiplied by the common ratio, which is 2 by 3, to the power of n minus 1. This is our final answer. So let's solve the next one. The nth term of geometric progression is 30 multiplied by minus half to the power of n. We have to find the first term and the common ratio. Let's find T1. T1 is 30 multiplied by -1 by 2. That's a -15. T2 will be 30 into minus half squared. That will be 30 by 4, which is 7.5. If we want to find the ratio, we do T2 divided by T1. So that's the ratio. And this is going to be 7.5 divided by -15. That's a -1/2. And the common ratio is therefore minus half. And if you want to find the first term, we already found it, so it's a minus 15. Therefore, A is minus 15 and R is a negative half. And now let's solve this question. We have to find the sum of the first 10 terms of the geometric series, 2 plus 6 plus 18 plus 54. We know that it's a geometric series, therefore A is 2 and R is 6 divided by 2, which is 3. Let's use the formula. R to the power of n minus 1 divided by R minus 1. A is 2 multiplied by what's R? R is 3. Therefore, we have to find the first 10, right? So 3 to the power of 10 minus 1 divided by 3 minus 1. If we solve this, we get 59,048. So this is our final answer. And let's solve the last question, which is related to the sum to infinity question. So the first 3 terms of a geometric progression are 25, 15, and 9. We have to write down the common ratio. So it's going to be 9 by 15, which is 3 by 5. And if we want to find the sum to infinity, we do this. A divided by 1 minus R. A is 25 divided by 1 minus 3 by 5. We get 62.5. So this is the answer. And with that, we're done with this whole chapter. At least 2 questions based on this chapter. Hence, this is very important. It's also as important as calculus. So you're going to get 2 questions. The first one is going to be a question related to the term independent of x, and then the other question will mostly be something related to either AP or GP. And yeah, with that we're done. Make sure you subscribe and leave a like.